solution is 50% sucrose, but what is it in molarity? That'll tell me how many moles are in a liter. But what if I want to know how many moles are in this tube? Or in a single milliliter? Or in a microliter? These tasks call for unit conversion. And so let's practice doing some calculations and thinking things through. Those reasonableness checks, as well as how to convert between weight volume percentage and molarity and moles and grams and all of this good stuff that we can do using unit conversion and the molecular weights and dimensional analysis and stuff. So let's do some practice. And yes, there are calculators that can do this stuff for you, and it can be really helpful, and it can actually be a good way to learn Python to actually write functions that do this for you and then check your work. But it's really important that you know how to do them yourself, especially because a lot of times in the lab you're having to do these kinds of calculations on the fly, on paper towels, on gloves, all of these various things, but then make sure you crunch them to your notebook. But anyway, it's really important that you know how to do them yourself rather than just rely on calculators. Plus, sometimes you might accidentally stick something in your calculator the wrong way or use the wrong sort of calculator, and so it's like one of those online tools. But it's important that you also be able to recognize whether your answers make sense. Do you expect numbers to get bigger or smaller when you're doing metric conversions? How can you make things simpler? Some various shortcuts, things like that. So I am in my drive. I have a Google Drive where you can find these various cheat sheets as well as the calculation examples. So the sodium chloride one I did the other day, and then this one with forms that have all of the answers, none of the answers, or some of the like hints, but not all the answers. So feel free to follow along, to watch the video afterwards, to not do anything. But if it's here if you want it, and so I hope it helps.
So to try to keep things short, I'm going to skip the background. If you are unfamiliar with metric prefixes or scientific notation or dimensional analysis, I will post links to posts there. You can learn about those. But today we're just going to dive in with this example of a 50% weight volume sucrose stock solution. So say you're tasked with preparing 200 milliliters of one of these solutions. Well, the first thing we need to do is know what weight volume percentage is, because it's one of these like percentages that isn't really a percentage. Basically, weight volume percentage means grams of solute per mils of solution times 100%, or I think an easier way to think of it is grams of solute per 100 mils of solution. So, for example, a 1% solution would be 1 gram per 100 mil. We want a 50% solution. So this would be 50 grams per 100 mil. But we want 200 mils. So there are a couple ways we can figure out how much we need. One is we can just recognize that 200 is twice as much as 100, and therefore we can just multiply 50 grams by 2 to get 100 grams, and this is going to tell us that we need 100 grams. Alternatively, we could work it out more formally with dimensional analysis, lining up the units and the conversion factors so that our units cancel out to give us the quantity that we want. So we know 50 grams per 100 mil, and we know 200 mils. We can line these up so that grams is going to be on the top because we want grams as our unit, not our over unit. And then we cancel out the milliliters, and this gives us the same answer that we need 100 grams. To actually prepare this solution, we then weigh out 100 grams, dissolve it in partial water, and then fill up to the volume, and then like filter sterilize it or something. So basically, it's important, especially when you're dealing with one of these really high concentration solutions, that you remember that the volume is going to be the total volume rather than the volume of your solute. So when you're, or solvent, sorry. So our solvent in this case is probably water, and for solute is going to be the sucrose. Now, 100 grams is a lot of sucrose. So if you're trying to stuff that much sucrose into water, 100 mils of water or 100 mil total volume, it will dissolve, but it's going to take up a lot of space. And therefore, you need to start with a small amount of water so that you don't overshoot and have too much volume. So you dissolve it in a smaller amount. Once it's dissolved, then you can add water to transfer to a graduated cylinder, add water to the fill line. And this will give you the total volume of, or fill it to 200 mils line, and this will give you the total volume of 200 mils and the solution at the percentage that you wanted, and more on preparing solutions in other posts. So that is in weight volume percentage. And again, it's not really a true percentage because your units aren't canceling out, but I'm not going to rant about that right now. What we care about more often is molarity. So molarity is talking in terms of copy numbers. And so how many moles per liter? So a mole, remember, 6.02 times 10 to the 23rd copies. And so molarity is 6.02 times 10 to the 23rd copies per liter. And so we like thinking in terms of copies because this is going to tell us about how many molecules might be interacting with one another and that sort of thing, rather than how much they weigh. Because you can think about a heavy molecule is going to be the same amount of copies of a heavy molecule is going to weigh a lot more than that amount of copies of a lighter molecule. So if you're just going 50% weight volume, then that's not going to tell you that much information about how many molecules are actually hanging out in the solution. So in order to get that sort of information, we need to know the molecular weight or the formula weight, which is going to tell us how much a mole of it weighs. We need to look up that molecular weight for sucrose. And we can just do this by looking on the bottle or by Google searching, and we find that it's 342.3 grams per mole. So this is going to allow us then to convert between the moles and grams. So moles, which is what we care about, and molarity is moles per liter, and then mass, the grams, what we can actually weigh out. Now we can calculate molarity. And so molarity, because molecular weight is going to be in, or because molarity is going to be in moles per liter, but our volume was given in milliliters. So we can either convert to liters beforehand, or we can do it explicitly in our dimensional analysis table. We line things up so that the units cancel out. So you can see that we're using this factor conversion. This conversion factor of 1,000 mils is 1 liter. And we line it up so that the mils are canceling out, leaving us with liters. And we get the value of 1.461 molar solution. As I mentioned before, sometimes it's easier to just like do some of the conversions in your head before putting them in the table. It makes things a little cleaner. So if you're looking, say, if you recognize that 100 milliliters is the same as 0.1 liter, because there are 1,000 milliliters in a liter, this is going to allow you to then just put in your volume in terms of liters, rather than having to stick it in terms of milliliters and then do this, use this conversion factor in your table, which then makes your table a little longer and potentially harder to read. But whatever works best for you, it's totally, totally valid. And sometimes maybe your teacher even will make you do it this way, where you actually explicitly put it in, and this can help you from making stupid errors as well. Okay, so how many moles of sucrose are there in 200 mils of a 50% weight volume sucrose solution? So we're talking about the same sucrose solution we just made. Well, how many moles are there? So we talked about molarity, which is moles per liter, but we don't have molarity, we have 200 milliliters. And so we could just say, okay, well, how many 200 milliliters are there in a liter? So a liter divided by 200 milliliters, so divided by 0.2 liters is 5. So we can divide 1.461 moles by 5, and this is going to tell us that we have 0.2922 moles. Alternatively, we could do this all with dimensional analysis in a couple different ways. So if we want to start from that molarity and the volume, we just calculated that molarity, which is telling us moles per liter, and we know the volume, which is in liters. And so we can just calculate, we line things up so that the units cancel out, and this is going to tell us that we have 0.2922 moles. Alternatively, if we don't want to go through that molarity explicitly, we can just do it inside of our dimensional analysis table, starting from the weight volume percentage and the volume, aligning things so that the units cancel out. And you can see that I've started by converting my units implicitly, or at least like mentally, into liters instead of milliliters to make my table a little easier to interpret here. But you can see that here we're calculating molarity within the table and not actually like announcing what the molarity is, but we get the same answer. So there are lots of ways to go about the same thing. depending on your starting information and what information you decide you want to start with, because all of these are kind of converting between the same numbers, and so there are different ways to go about things. And no, one is not better or worse than the other in a lot of cases. It's just whatever's convenient and whatever makes sense to you. Just make sure that your units are always canceling out, leaving you with the value that you want, and then doing reasonableness checks. So now write this in a form that avoids putting all the decimals after the decimal, all the values after the digits after the decimal place. So 0.2922 be kind of hard to work with and not that easy to think about. So if we write this in a form that uses a metric prefix that allows us to make it easier to work with, what would be the best metric prefix to use? So because our metric prefixes are basically going in terms of 1,000, we can move our decimal places by like 3 to the left or 3 to the right to go between different scales. So the most convenient would be to go to 3 to the right. If we're going to the right, so we're making our number bigger, this means that we're going to be thinking in terms of smaller units. So it's like we're thinking in terms of how many pizza slices do we have rather than how many pizzas do we have. So if we think about pizzas, then we're going to have fewer pizzas. If we think about pizza slices, we're going to have more slices. So if we think about the same amount of stuff with a smaller unit size, we're going to have a larger number. So we want to think about a smaller unit size. So what's 1,000? What's going to take us about 1,000 volts? So what's going to take us 3 to the right in terms of our decimal place? This is going to take us from moles to millimoles. So our millimoles, like our pizza slice in this case, and then our moles, like a pizza. And so you can see that there are 1,000 milliliters or 1,000 millimoles in a mole, because that milli means 1,000. So we can multiply this by 10 to the third. We're going in here, and we're getting 292.2 millimoles. Okay, so how many moles of dissolved particles? I say this because when we talked about sodium chloride, we saw how sodium chloride didn't just dissolve, it dissociated. So it split up into component ions, sodium and chloride ions. So we got twice as many particles as we put in. So say you put a mole of sodium chloride in, and now you get a mole of sodium ions and a mole of chloride ions. If you look at sucrose, you can see it's made up of glucose and fructose, but these are combined by a strong bond, a covalent bond. So this is not going to break up just because you dissolve the molecule. Instead, when you dissolve the molecule, this whole thing is going to get a coat of water. So the amount of particles that you get when you dissolve sucrose is going to be the same as the amount of particles as you put in. And this comes into play because of things like colligative properties. More on that in the post on the sodium chloride. But here we're getting the same amount of moles as we put in, which would be 0.2922 moles, or which, as we saw, we could write as 292.2 millimoles. Okay, so that was how many total moles, but how many moles of sucrose per milliliter? And again, there's going to be several ways we could do this. So one way, so we know the molarity of our solution. We determined it was 1.461. This means that there are 1.461 moles per liter, and we want moles per milliliter. So a milliliter is smaller than a liter, so we're talking about this stuff in a smaller volume. So it's like thinking about how many slices of pizza are in a single box versus how many slices of pizza are in a carrier bag full of pizza boxes. So we're going to get a smaller number. How much smaller? Well, 1,000 volts, because the milliliter is 1,000 times smaller than a liter. So now we're going to move our decimal place 3 places to the left to give us 0.001461 moles per milliliter. Another way to think about this is that we know the molarity is 1.461, so 1.461 moles per liter. Now this is the same thing as saying 1.461 millimoles per milliliter. Why? Because we can change the units by dividing the top and the bottom by the same number. So here 1,000. So we're dividing the moles by 1,000 and the liters by 1,000. So 1,000 over 1,000 is 1. This is the whole idea of dimensional analysis, is that we could multiply or divide things by 1 without changing the actual thing. So we can change the units. We're changing both of these. So we're going from moles to millimoles and liters to milliliters. So we can say that 1.461 moles per liter is the same as 1.461 millimoles per milliliter. So by similar logic, 1.461 molar is also the same as 1.461 micromole per microliter, or nanomoles per nanoliter. So we have 1.461 millimoles per milliliter. Now, if we wanted to have that as a value in terms of moles, instead of millimoles, Well, now, okay, so now we're gonna have, this is like thinking, okay, how many pizza boxes, how many full pizzas do we have, or how many pizza slices do we have? So we're gonna get a smaller number. So we're going to have to divide the number of millimoles by 1,000 to get back to moles, and divided by 1,000 is the same as multiplying by 10 to the negative third. So we could write this either like this, or in terms of the decimal, and we can just move our decimal place. Similarly, okay, so yeah, reasonableness stressors, as we just talked about, our number should be getting smaller because we're talking about the same amount of stuff, but in terms of bigger units. And so as we just saw, we got a smaller number, so that all checks out. We can also use dimensional analysis to do all of this from the starting info from that weight per volume percentage without going through any intermediate steps. Okay, now similarly, we could do the same sort of thing to figure out how many moles of sucrose per microliter. So here, instead of 1,000th, we're dealing with a millionth, but we can do the exact same thing and get an answer that's the same. We can also recognize that there's 1,000 microliters in a milliliter. Start with that milliliter volume value and then move our decimal place 3 places to the left from that. So going from micro to milli, other than micro to the base. So micro to milli, that's a factor of 1,000. Micro to the base, that's a factor of 1,000,000. We could also do this, think about it the same way we saw above, where 1.461 moles per liter is the same as 1.461 micromole per microliter because we're dividing the top and the bottom by the same amount. And we could do this with dimensional analysis. Just a quick reasonableness check. Our numbers get smaller when we think about the number of molecules in smaller volumes. So fewer pizza slices in a single box of pizzas than a carrier box full of pizzas. And our number was getting smaller, so that checks out. So a key shortcut to recognize is that when you're dividing the top and the bottom by the same conversion factor, so making moles and liters, millimoles and milliliters, or micromoles and microliters, they're both the same prefix. They both still have the same prefix. So if we start in terms of moles per liter, that will also be millimoles per milliliter, micromoles per microliter, nanomoles per nanoliter, etc. It's the ratios that matter, and they stay the same if we add the same prefix. And hope that helped. And check out the sodium chloride example if you want some more practice.